All right, so today we are going to be talking about light. Now, we have talked about waves and different types of waves before. We've talked about sound in the context of waves. Now we are going to talk about light and its wave-like behavior. So our objective for this video is to be able to identify characteristics of a light wave and calculate the velocity, frequency, and wavelength of a light wave. Your essential question that you all should be answering in about a 1 to 2 sentence summary down at the bottom of your notes is, what is a light wave and how fast does it travel? So we're going to zoom in a little bit on our mind map notes, and let's just start off with that simple question of what is light? All right, so there are different theories that have tried to understand what light exactly is. So in this video, we are going to be talking about light and referring to light as a wave, as an example of a wave. But later this year, we will talk about the quantum theory of light, which explains that light is both a particle and a wave. Now, I don't want to blow your minds just yet, so we are going to be, again, just talking about light's wave-like behavior in this video. And we know that we have two different types of waves. We learned those two different types of waves from previous videos. We have mechanical and electromagnetic waves. Now, light is an example of an electromagnetic wave, meaning it does not need a medium or a substance to travel, right? Light can travel through space. That's how we get light during the day on Earth, right? Thankfully, the light is able to travel through space from our sun to come to Earth. Now, diving a little bit more into this concept of the electromagnetic waves and electromagnetic spectrum. This is the spectrum of different electromagnetic waves. And you can see that light falls in a very narrow portion of this electromagnetic spectrum, right? So starting with the longest wavelength over to the left, we have radio waves, right? These are waves that you all use if you ever play the radio in the car. We use radio waves all the time to communicate over the radio. All right, on the opposite end of the spectrum with a super short wavelength, but a very, very high frequency, we have gamma rays. Now, if you all are superhero fans, you know that gamma rays are very high energy. Bruce Banner, our Incredible Hulk, exposed himself to gamma rays in the Marvel universe, right? So these are very high energy, very, very dangerous electromagnetic waves. Thankfully, visible light does not fall in that category. Visible light is lower in energy even than UV rays, but we also know how powerful UV rays are because those are the rays from the sun that give us those really bad sunburns if you stay out in the sun too long. So within our very narrow region of visible light, we have our different colors. So if you recall us mentioning in class, the frequency of the visible light and the wavelength of visible light affects the color that we see. So our lowest frequency on the left side of this spectrum and our lowest energy light waves are going to be the color red, right? So these are red waves, low frequency, low energy, but longer wavelength. And on the opposite end of that visible light spectrum, we have our super high frequency, high energy waves, which are our violet light waves. So within this small little wavelength of visible light along this electromagnetic spectrum, we can break it down even further to see these various colors. All right, so that's kind of an introduction into what light is. Now let's talk about how fast light travels. All right, so we are going to go through a quick example about how to calculate light. But one thing I do want to point out is that we are going to learn a new constant here. Now remember, a constant is something that does not change. All right, so I'm going to write out that C is a constant. So unlike a variable, a constant represents a number that will never change. So the constant that we are learning today is the speed of light in a vacuum, which we use the letter C to represent the speed of light in a vacuum. C is always going to be equal to 3 times 10 to the 8th meters per second, right? So that is super, super fast. Now, this is, again, speed of light will change depending on the medium it is traveling through, right? We know that light is faster through air than it is through water. The fastest light will ever be, though, is in a vacuum. So in space, for example, light is traveling at a speed of 3 times 10 to the 8th meters per second. Now, I do want to point out that we are going to be using scientific notation for some of these numbers because they are such big numbers. So anytime you see something times 10 with an exponent on it, this is scientific notation. So it is really just sometimes in science we have to work with big numbers. So we are just making it a little bit easier on ourselves to write it out. All right. Our equation that we are using with the velocity or speed of light is going to look very similar to our normal wave equation, all right? So all we are doing is replacing our normal wave equation, which is V equals lambda F, right? We are replacing that V, which for normal waves we know can change, right? We know the velocity of a wave can change depending on its wavelength and its frequency. We're replacing that variable V with the constant C, understanding that the constant C is always going to be 3 times 10 to the 8th meters per second for our speed of light, all right? So this is our general wave equation. V equals lambda F. This highlighted equation is our equation for light in particular. All right, so thankfully it is still a 3-variable equation, so we can actually use our triangle trick for this calculating various aspects of light. So we're going to go through a quick example right now of using this triangle trick. All right. So this problem says violet light has a wavelength of 4.1 times 10 to the negative 12th meters. Calculate its frequency. So again, we're using this scientific notation. What this is really saying, if we were to put this in standard notation, is that its wavelength is 0.1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, all right, meters long. So that is a lot of writing. And again, this is standard notation, all right? So this is scientific notation with the 10 and the exponent. This is standard notation. So again, scientists, we don't like to do a lot of writing. So that's why we are using scientific notation for some of these numbers. All right. So let's go ahead and start our 4 steps with solving a physics word problem. First thing I'm going to do is draw out a violet colored wave. Now we'll get that going. right now. All right, so we know that its wavelength is super, super small. So just to depict that, I'm going to draw out a wave with a super small wavelength to indicate that it is going to be teeny, teeny, tiny. All right, so that is the wave here. Moving on to step number 2, we're going to write out what we know and what we don't know. Okay, so starting off with what we do know. All right, we do know that, I'm going to do this in a different color here. We know that violet light has a wavelength of 4.1 times 10 to the negative 12th. All right, so I can write out that lambda, which is the variable we use for wavelength, is equal to 4.1 times 10 to the negative 12 meters. All right. The other thing that we know and that we always know is what our speed of light is, and that is a constant. So we always know that the speed of light, right, C for speed of light, is always going to be equal to 3.0 times 10 to the 8th meters per second. So this problem is giving us one number. We always know the other number, which is the speed of light. And it is asking us to calculate the frequency of the wave. So I'm going to write out that F for frequency is a big question mark. We don't know what frequency is equal to. All right, moving on to step number 3, let's go ahead and write out our wave or speed of light equation, which is C equals lambda F. Now, here is where we need to shuffle things around. At the moment, this equation does not solve for frequency, right? So we need to change this equation up so that frequency is by itself on its own side of the equal sign, indicating that we are solving for frequency now. So again, we can actually move over to our triangle here. So remember, when we have our triangle trick, we are going to cover up whatever we don't know on the triangle. So we know that we don't know frequency at the moment. We're solving for frequency. So with your finger, with your hand, you can cover up that thing that you don't know on the triangle. And that gives us an equation that kind of looks like this, equals C over lambda. So we are going to rearrange this equation so that it solves for frequency, which will give us C over lambda, right? Now that we've got that equation set up, it is solving for frequency. We can go ahead and start plugging some things in. So first thing we're going to plug in is, I highlighted that in the wrong color. First thing we're going to plug in is our speed of light, right? So our speed of light is 3.0 times 10 to the 8th meters per second. Keeping all other operations in this equation the same, then we can go ahead and plug in our wavelength for violet light, which we know from the problem is 4.1 times 10 to the negative 12th meters, right? Now that we've got that set up, we can go ahead and plug this in our calculator and solve. So quick thing though is that since we are using scientific notation, right, we want to make sure we are following the correct order of operations here. So we know that these numbers need to stay together, because what this is really saying is that 3 times 10 to the 8th or 4.1 times 10 to the negative 12, that is one number. but we're using scientific notation to break it up so that it's a little bit easier to write. So if it's one number, we want to make sure that it stays one number. So we're going to group these into parentheses. This will just help as we type it in our calculator to indicate that this needs these this 3.0 and this 10 to the 8th need to stay together as we solve using PEMDAS. Now, if you were to type it in the calculator correctly, you all should get a frequency of 7.3 times 10 to the 19th hertz. All right, so that is a very, very high frequency. Again, 10 to the 19th, that is a very, very large number. All right, but that does indicate something about the frequency of violet light. Remember from the beginning of this video, we talked about how violet light has a very, very high frequency, and we have just proven that through our calculations here. All right, moving on to a couple other unique characteristics of light. And while these are all things that can happen to all different types of waves, they kind of, they're easier to kind of see when we use the example of light and depicting them through light. So again, all waves can demonstrate reflection, right? But this is most often seen when we put it in the context of light. So the first thing that is a really cool characteristic of waves, and in particular light, is that they are able to reflect, right? They are able to strike a surface and bounce back off of that surface. Easiest example of reflection is when you look at yourself in the mirror. When you look at yourself in the mirror, these waves, these light waves, are bouncing back at you, which allow you to see your reflection there. So that's a really cool way that we use light and the reflection of light to be able to see ourselves in the mirror. Another cool characteristic of light is something called refraction. So refraction is when, I'll highlight that. Refraction is when there is a change in a wave's speed as it travels through two or more different types of mediums. So we see this most often when we place an object in water. If you've ever placed a pencil in water, for example, here's another example of refraction here. I'll draw a cup of water. That's not a very good cup. Here's our cup of water, right? If you've ever placed a pencil in here or a pen or something in that cup of water, or even if you've placed a straw in there, right? It almost looks like it's changing position. Kind of starts to change that. It looks different and like it's in a different position underwater than it does above water. That is an example of refraction. That's a result of the change in light's speed from air into water, right? The index of refraction is kind of coincides with this idea of refraction. It is a measure of how much a wave's speed is reduced in a medium. So between air and water here, the index of refraction is pretty high in water, meaning that light travels a lot faster in air than it does in water. So we're going to see this really unique effect on these objects when they travel, or when they're depicted using light from the air into the water. So those are examples of refraction here. Another cool characteristic of light waves is they're also able to have diffraction. And again, all waves have diffraction, okay? So even ocean waves have diffraction, but the way that light waves are used in this example is pretty neat. All right, so diffraction is when a wave bends around an obstacle. So if you were to shine a light through this narrow little slit here, you would actually start to see the light kind of bend, really. And we'll go through an example of how this diffraction and this property of light is used in just a moment. But we see this in ocean waves all the time, right? We have these curved coastlines, okay? If you've ever been to the coast, right? We have these curved coastlines. Here's our ocean. And what's happening here is that these ocean waves, they hit this point in the coast where it's a narrower slit of coastline, and they started to form and erode these different areas of the coastline. So that's another example of diffraction as well. We also have something called interference, all right? And this plays out in a pretty unique way when we use it in the context of light and light waves. But again, all waves experience interference. So this is when two waves meet while traveling in the same medium. Now we have two different types of interference. We have constructive and destructive. So you can kind of see the difference just by looking at these depictions. Constructive happens when these waves that are colliding are in phase with one another, meaning their crests and troughs line up. And as a result of this constructive interference, you actually end up with a larger waves, a wave with a higher amplitude, right? That's constructive interference. In contrast, we have destructive interference, which means the waves are out of phase. So when these waves collide, it actually just results in no amplitude at all. So that's the difference between constructive and destructive. Now, with these two final concepts of diffraction and interference, a scientist named Thomas Young was actually able to prove that light is a wave using diffraction and interference. So this is Young's double slit experiment. We'll talk about this a little bit more if we get to our quantum unit of light and discussing how light is both a wave and a particle. But this was a really, really important experiment that proved that light does have wave-like properties. So what Young did is that he used a light source. So we could say this is a flashlight here that he's using. All right, so he used a flashlight to create these light waves. And I'm drawing these light waves in red here. So these light waves are traveling toward this first barrier, which is in blue. And you can see Young left two little slits in this barrier. Everything else is a wall, but these two little slits in this barrier allowed these white light waves to continue traveling through the slits and start to diffract. Now, since there are two of them, we started to see some interference between these light waves and this diffraction. Now, after this barrier with those two slits, Young placed another flat surface. We could say this was a wall, so that he could see the result of the light traveling through this double slit, these two different slits. And what he saw was this pattern along the wall. And it's a really cool pattern because before then, we would have just assumed that all of the light would have just made it to the wall, right? But we actually started to see this pattern that resulted from constructive and destructive interference on the wall with the waves of light. So if light was simply just a particle, we would have actually seen something like this on the wall, where the entire wall has been lit up by light. I'll draw this in just as soon as I can get my highlighter out. So the entire wall would have been lit up here. All right, but in contrast, we saw this really unique striped pattern, which proved to scientists at the time that light had a wave-like property, because these large areas of light, this thick area of light, so anytime you see this red little dash here, this was a result of the constructive interference between those light waves. Anything in between those red dashes would have been dark spots, and those dark spots were the result of destructive interference of light waves. So again, I'm not going to quiz you all on the ins and outs of Young's double slit experiment, but I think it is a really cool experiment that was really groundbreaking at the time to prove that light was in fact a wave. So hopefully this gives you all a cool little preview of different aspects of light and how light behaves as a wave. As always, please make sure you all, after watching this video, write a 1 to 2 sentence summary answering that essential question about what light is, how fast it travels, and maybe you can include some unique characteristics of light in there as well. I look forward to discussing this with you all more in class.